Somewhere right now, in a quiet room, a brain made of roughly 86 billion neurons is doing something no instrument on Earth can fully explain. It is producing the soft, continuous, private experience of being someone, not just processing information the way a calculator processes numbers, but feeling the warmth of a blanket, or the color of a lamp across the room, or the faint drift of a thought arriving from nowhere in particular. This is consciousness, and it is, by a wide margin, the strangest thing we know about. It is worth sitting with that for a moment before going any further. We are used to thinking of the universe as something we observe from the outside, a vast mechanism of stars and gravity and chemistry that goes on whether or not anyone is watching. And for almost everything in that mechanism, that picture works well. Rivers do not need to be experienced to flow. Chemical reactions do not require a witness to occur. But somewhere inside certain arrangements of matter, on at least this one planet, something else appears to be happening. Matter is not just moving. It is, in some sense, aware that it is moving. This program is about that puzzle and about the different ways thoughtful people across history and into the present have tried to make sense of it. Some of those ideas come from careful science, laboratories studying brain activity, physicists studying the strange behavior of particles, philosophers drawing precise distinctions between what can and cannot be tested. Other ideas are older and more speculative, rooted in ancient philosophy or mystical tradition, proposing that mind is not something confined to skulls, but something woven into the fabric of everything. None of these ideas has been proven. Some are taken seriously by working scientists and philosophers. Others are considered fringe or metaphysical, sitting outside what current evidence can settle one way or the other. Part of what makes this topic so interesting is figuring out which is which and being honest about the difference. We can start with the plainest version of the puzzle, the one philosophers call the hard problem of consciousness. The phrase was introduced in the 1990s by the philosopher David Chalmers as a way of separating two very different kinds of question about the mind. There are what he called the easy problems. How does the brain focus attention? How does it store a memory? How does it integrate signals from the eyes and ears into a single scene? These are called easy, not because they are simple to solve. They are in fact enormously difficult, but because we know, in principle, what a solution would look like. It would look like a description of some mechanism, some circuit or process that performs the function in question. Neuroscience has made real progress on many of these questions, mapping which regions of the brain light up during attention or memory formation or visual processing. The hard problem is different. It asks why any of that processing is accompanied by experience at all. Why does the integration of visual signals in the brain come with the feeling of seeing red, rather than simply happening in the dark, so to speak, with no one home? Philosophers call the subjective, felt quality of an experience its qualia, from the Latin word for qualities. The redness of red, the specific ache of sadness, the taste of salt on the tongue, these are qualia, and the puzzle is that no description of neurons firing in a particular pattern seems to explain by itself why that firing should feel like anything from the inside. You can describe the wiring in complete detail and still have not explained why there is a subject there to notice it. This is not a problem most other sciences face. If you want to explain why water is wet, or why a certain gene produces a certain protein, you break the phenomenon down into simpler physical components. And once you have accounted for the components, the phenomenon is explained. Water's behavior emerges from the properties of hydrogen and oxygen atoms and how they bond. Consciousness has resisted this kind of reduction. Break the brain down into neurons. Break the neurons down into molecules. Break the molecules down into atoms. And at no point does a description of the physical parts, however detailed, seem to logically require that the whole thing feels like something. This gap between physical description and subjective experience is what makes consciousness such a stubborn scientific and philosophical target, and it is why, after centuries of study, we still do not have a settled answer to what consciousness fundamentally is, where in nature it begins, or why it exists at all. It helps to notice that this is not a new question. Even though the term hard problem is fairly recent, people have been circling this same puzzle in different language for as long as they have been thinking carefully about themselves. Long before anyone had a word for neurons, philosophers in ancient Greece, in India, in Persia, in China, were asking what the mind was made of and how it related to the body, and whether it was something separate from ordinary matter, or simply another kind of ordinary matter, organized in an unusual way. Over the centuries, this question branched into a handful of broad positions, each with its own long lineage of thinkers, and it is worth walking through that history slowly, because the modern debate about consciousness and the universe still rests on these old foundations. The most famous historical position is dualism, most closely associated with the French philosopher René Descartes. Writing in the early 1600s, Descartes proposed that reality is made of two fundamentally different substances. There is physical substance, extended in space, following mechanical laws, which makes up rocks, bodies, and brains. And there is thinking substance, which is not extended in space at all, and which is the seat of consciousness, reason, and the self. On this view, the mind is not the brain. The mind interacts with the brain. Somewhere, Descartes speculated it might be the pineal gland, but the two remain distinct kinds of thing. Dualism has an obvious appeal. It matches how consciousness feels from the inside, private, immaterial, unlike anything else we bump into in the physical world. But it has an equally obvious problem, one that philosophers have pressed on ever since. If mind and matter are truly different substances, how do they interact at all? How does an immaterial thought cause a physical arm to move? Descartes never gave a fully satisfying answer, and this interaction problem is a major reason most contemporary philosophers of mind have moved away from strict dualism, even though it remains intuitive to many people in everyday life. The opposing tradition is materialism, sometimes called physicalism, which holds that everything, including the mind, is ultimately physical. On this view, consciousness just is a certain kind of physical process, likely something happening in the brain, and once neuroscience is complete enough, there will be nothing left over to explain. Many working scientists lean toward some version of physicalism because it fits comfortably within a broader scientific picture where everything, in principle, reduces to physics. But physicalism runs directly into the hard problem described earlier. Even a complete physical description of the brain's wiring does not, on its own, seem to explain why that wiring is accompanied by felt experience. Some physicalists respond that this feeling of an unexplained gap is itself an illusion, a kind of cognitive blind spot, and that once we understand the brain well enough, the mystery will simply dissolve. The way vitalism, the old belief that life required some special non-physical spark, dissolved once biochemistry explained metabolism and reproduction in ordinary physical terms. Other physicalists are less confident that consciousness will dissolve so neatly and think the hard problem points to something physicalism has not yet reckoned with. A third tradition, older in some ways than either of the first two, is monism of a different flavor, the idea that mind and matter are not two separate things, and not simply matter alone, but two aspects or expressions of one underlying reality. The 17th century Dutch philosopher Baruch Spinoza is the figure most associated with this view in the Western tradition. Spinoza argued, in his work titled Ethics, that there is only one substance in the universe, which he sometimes called God and sometimes called nature, and that thought and physical extension are simply two different attributes of that one substance, two different ways of describing the same underlying reality. On this view, a rock and a thought are not different kinds of thing at a deep level. They are different expressions of a single, unified nature, and everything that happens by the necessity of that nature rather than by pure chance. Spinoza's system was radical for its time and was condemned by many religious authorities, but it quietly influenced later thinkers, including some of the philosophers who developed early versions of Panpsychism, the idea we will spend a good deal of time with later in this program. Alongside dualism, materialism, and Spinoza's dual-aspect monism, there is a fourth broad family of positions, sometimes called idealism, the view that mind or experience is the fundamental substance of reality, and that the physical world is in some sense derived from or dependent on mind, rather than the other way around. Idealism has deep roots in several traditions. In classical Greek philosophy, Plato argued that the physical world we perceive with our senses is a shifting, imperfect copy of a more fundamental realm of unchanging, eternal forms, which the intellect, rather than the senses, can grasp. In the Indian philosophical tradition, certain schools of Vedanta describe the physical world as appearance layered over a single underlying consciousness. In 18th century Europe, the Irish philosopher George Berkeley argued that physical objects only exist as they are perceived, a position summarized in the phrase to be is to be perceived. Idealism in its various forms has never been the dominant view among working physical scientists, largely because it is difficult to test and because ordinary physical science has been so successful working under the opposite assumption that there is a mind-independent physical world for our theories to describe. But idealism has never fully disappeared either, and versions of it resurface, sometimes in updated and technical form, whenever physics runs into deep puzzles about the role of observation and measurement, a thread this program will pick up later when discussing quantum mechanics. It is worth pausing here to distinguish careful academic philosophy of mind from another kind of tradition that sometimes gets blended in with it in popular discussion, esoteric and mystical systems such as Hermeticism, a body of teachings that developed in the Eastern Mediterranean in the first few centuries of the Common Era, traditionally attributed to a legendary figure called Hermes Trismegistus. Hermetic writings describe a set of guiding principles, often summarized in later centuries as sayings like the principle of mentalism, the idea that the universe is fundamentally mental in nature, or the maxim as above, so below, suggesting a correspondence between small and large scales of reality. These ideas have had a long cultural life, influencing alchemy, certain strands of Renaissance philosophy, and later esoteric and New Age movements. They are genuinely interesting as intellectual history, and they touch some of the same questions as academic philosophy of mind, but it is worth being clear that they are not scientific theories in the modern sense. They were not developed through controlled observation or open to empirical testing in the way integrated information theory or quantum mechanics are, and contemporary scientists do not treat hermetic maxims as evidence about the nature of consciousness. They belong to the history of ideas about mind and cosmos, not to the body of tested science about it, and this program will treat them accordingly as historical and cultural context rather than as findings. With that groundwork laid, we can turn to how modern science, rather than ancient or esoteric philosophy, has actually tried to get a grip on consciousness, and the most direct approach, unsurprisingly, has been to look at the one organ we know, with high confidence, is deeply involved in producing it, the brain. The brain is, by any measure, an extraordinary object. It weighs a little under 1.5 kilograms, roughly 2% of the body's total weight, and yet it consumes something like 20% of the body's energy at rest, an enormous metabolic cost for something that does not move the way muscles do. It contains on the order of 86 billion neurons, each one connected to thousands of others, forming a network with more connections than there are stars in the Milky Way galaxy. Understanding how this network gives rise to a unified, felt experience has been one of the central projects of neuroscience for the past several decades, and it has produced a great deal of solid, well-tested knowledge, even if the hard problem itself remains unresolved. One useful line of evidence comes from patients who have had the connection between the two hemispheres of the brain surgically severed, a procedure historically used, rarely, as a last resort treatment for severe epilepsy. The band of tissue connecting the hemispheres is called the corpus callosum, and cutting it produces what are known as split brain patients. Studies of these patients, carried out in the 1960s and beyond by researchers including Roger Sperry and Michael Gazzaniga, revealed something remarkable. Information presented only to one half of the visual field, and therefore processed only by one hemisphere, could be acted on by that hemisphere without the other hemisphere having any conscious knowledge of it. In some experiments, the left hand, controlled predominantly by the right hemisphere, would pick up an object the patient's verbal left hemisphere could not identify or explain, and the left hemisphere would sometimes construct a plausible-sounding but incorrect story to explain the hand's behavior after the fact. These studies suggested that ordinary, everyday consciousness, the sense of being one unified self, depends on a great deal of integration between brain regions, and that when that integration is disrupted, something like two semi-independent streams of awareness can result, each with a partial and different picture of the world. Another important body of evidence comes from anesthesia research. Modern surgery depends on being able to reliably switch consciousness off and back on again, and anesthesiologists have learned a great deal in practical terms about which brain states correlate with the presence or absence of awareness, even without a complete theoretical explanation of why. Different anesthetic drugs act on different neural targets, but a common finding is that loss of consciousness under anesthesia correlates strongly with a breakdown in the complex, integrated communication between different regions of the cortex, even when local, isolated brain activity continues. Researchers led by Marcello Massimini and Giulio Tononi, whose broader theoretical work we will return to shortly, developed a technique combining magnetic brain stimulation with electroencephalography, essentially pinging the brain with a magnetic pulse and reading out how the resulting activity spreads and echoes across the cortex. In waking, conscious states, That ping produces a complex, far-reaching differentiated pattern of activity under deep anesthesia, or during dreamless sleep, or in certain disorders of consciousness following brain injury. The same ping produces either a simple, undifferentiated response or one that fails to spread beyond its local starting point. This measure has since been developed into a practical clinical tool, sometimes called a perturbational complexity index, used to help assess residual consciousness in patients who cannot behaviorally respond, such as those in a vegetative state or minimally conscious state, a genuinely important application growing directly out of theoretical consciousness research. A further important thread concerns dreaming and sleep more generally. During most of the night, the sleeping brain cycles through several distinct stages, including deep, slow-wave sleep and what is called rapid eye movement sleep, or REM sleep, during which the eyes move rapidly beneath closed lids and most vivid dreaming occurs. Brain imaging shows that during REM sleep, many regions of the cortex are almost as active metabolically as during ordinary waking, even though the sleeper is, by ordinary behavioral measures, entirely unconscious of the external world and, upon waking, often reports having experienced a vivid, if usually strange and disjointed, inner world. This tells us something important. Consciousness is not simply a matter of overall brain activity, being high or low. It depends on the pattern and organization of that activity, on how information is integrated and connected, rather than on sheer quantity of neural firing. A brain can be highly active, and yet, depending on how that activity is organized, produce anything from ordinary waking awareness to dream consciousness cut off from the senses to no reportable experience at all. These findings, taken together, point toward a recurring theme that runs through much of modern consciousness science. What seems to matter is not any single brain region acting as a control center, nor any particular chemical, but the integration, the binding together, of information across a widely distributed system. This theme is exactly what the most influential scientific theory of consciousness in recent decades, integrated information theory, tries to take seriously and formalize into something closer to a precise, testable proposal. It is worth spending real time with this theory, both because of its influence and because it will resurface, in modified and sometimes questionable form, in later discussions about whether consciousness might extend beyond brains altogether. Integrated information theory was developed primarily by the neuroscientist and psychiatrist Giulio Tononi, building on decades of work studying sleep, consciousness, and brain connectivity at the University of Wisconsin. Tononi's starting point was somewhat unusual for a scientific theory. Rather than beginning with the brain and asking how its physical mechanisms might produce experience, working from the bottom up, he began with the felt properties of experience itself and asked what physical system would need to look like in order to have those properties. Working from the top down, he identified two properties that seem to characterize any conscious experience, however simple or complex. The first is what he called differentiation. Any given conscious experience is one specific experience out of an enormous number of possible experiences you could have had instead. Right now, whatever you are experiencing, whether it is a memory, a sound, a passing thought, it rules out an immense space of alternative experiences you are not having. That specificity, that being this particular experience, rather than any of countless others, carries a great deal of information in the technical sense that information theorists use the term, meaning a reduction in uncertainty among possibilities. The second property is integration. A conscious experience is not simply a bundle of independent parts, like a collection of separate photographs stapled together. It is unified. When you look at a scene, you do not experience the color, the shape, the motion, and the sound as separate, disconnected streams that happen to occur at the same time. You experience one unified scene. This suggests that whatever physical system underlies consciousness must integrate information across its parts, such that the whole carries more information than the sum of its independent pieces would carry on their own. From these two properties, differentiation and integration, Tononi and his collaborators developed a mathematical framework intended to measure how much integrated information a physical system generates, denoted with the Greek letter phi. Very roughly, phi asks how much a system's causal structure, the way its parts influence one another, resists being broken down into independent, non-interacting components without losing information. A system with a high phi value has a highly integrated causal structure that cannot be decomposed into separate parts without a significant loss of information about how the system behaves. Integrated information theory proposes, as its central and most controversial claim, that the amount of consciousness a system has corresponds to how much integrated information, how much phi that system generates, and that the particular quality of the experience, what it is like, corresponds to the detailed structure of that integrated information, sometimes described using a geometric picture theorists call qualia space. This theory has several features that make it distinctive among approaches to consciousness. First, it does not require a system to behave in any particular observable way, to speak, or to move, or to solve problems, in order to have some degree of consciousness. What matters is the internal causal structure, whether information is genuinely integrated rather than merely processed in parallel, independent channels. Second, and this is the feature that has generated the most public discussion and controversy, the theory implies that phi, and therefore some non-zero amount of consciousness, could in principle be calculated for any sufficiently integrated system, not only brains. A sufficiently interconnected computer chip, in principle, could have some non-zero phi value, though current digital computers, built from architectures optimized for fast information processing rather than integration, are generally thought to have very low phi despite enormous computational power, because most of their internal information transfer happens through simple, feed-forward, easily decomposable channels rather than densely interconnected, irreducible ones. This is one of the theory's more interesting and sometimes misunderstood predictions. It does not straightforwardly imply that today's artificial intelligence systems are conscious, because the internal architecture of most current systems, however capable at producing intelligent-seeming output, is thought to have relatively low integration in the technical sense the theory requires. Whether future computing architectures, deliberately designed with much higher integration, might have significant phi remains an open and actively discussed question among theorists working in this area. Integrated information theory has been influential, but it is not universally accepted, and it is worth being honest about the state of the debate rather than presenting it as settled. Critics have raised several serious objections. One is a practical one: calculating phi exactly for any real, complex system, including a brain, is computationally intractable because it requires considering an astronomically large number of ways the system's parts could be partitioned. In practice, researchers use approximations and simplified proxies rather than the exact quantity, which limits how directly the theory's central claims can be tested against real neural data. A second objection, raised prominently by the philosopher Scott Aronson, a computer scientist working on computational complexity, is that the theory's own mathematics seems to imply that certain very simple, almost trivially structured systems that intuitively should not be conscious at all, such as certain error-correcting grids of interconnected logic gates, could nonetheless have extremely high phi values, arguably higher than a human brain. If a theory implies that a simple grid of logic gates is more conscious than a person, critics argue this counts as evidence against the theory, or at least against taking its numerical predictions completely literally, rather than as evidence that such grids really are richly conscious. More recently, in an unusually direct piece of scientific self-correction, integrated information theory was tested directly against a rival theory of consciousness, global workspace theory, which we will discuss shortly, in a large, pre-registered, adversarial collaboration involving multiple independent laboratories around the world, coordinated through a project sometimes called the Cogitate Consortium and reported in the mid-2020s. The results were genuinely mixed, and notably, they did not straightforwardly vindicate either theory as originally formulated. Some predictions specific to integrated information theory were not supported by the data, and some predictions specific to global workspace theory were also not supported. Both theories' proponents have since revised aspects of their proposals in response. This is worth dwelling on for a moment because it illustrates something important and honest about where the science of consciousness currently stands. Despite decades of serious empirical work, there is not yet a single, agreed-upon, well-confirmed scientific theory of what consciousness is or exactly which physical systems have it. There are several serious, actively researched candidate theories, integrated information theory among them, each capturing real and important aspects of what consciousness seems to involve, and each facing real, unresolved challenges. Anyone who tells you the question is settled in either direction is telling you more than current science actually knows. It is exactly this open, unsettled quality of the scientific picture that creates room for much more speculative extensions of these ideas, extensions that go well beyond what the original scientific theories claim, and it is here that we start to move from careful, if incomplete, neuroscience into the more philosophically adventurous territory of panpsychism, the idea that consciousness, or something like it, might not be limited to brains at all, but might instead be a much more widespread, perhaps even universal, feature of the physical world. Panpsychism, in its broadest sense, is the view that mind, or some very basic precursor of mind, sometimes called proto-consciousness or experience in a minimal sense, is a fundamental and ubiquitous feature of physical reality, present in some form even at the level of the smallest constituents of matter, rather than something that only appears once matter is organized into brains. It is one of the oldest ideas in the philosophical study of mind, and it is important to say clearly at the outset that it remains a minority position among philosophers and an even smaller minority position among physical scientists, though it has seen a genuine resurgence of serious academic interest over the past 2 or 3 decades, discussed by professional philosophers in peer-reviewed journals, rather than only in popular or mystical contexts. Its roots go back to the earliest Greek philosophers, whose writings survive even in fragments. Thales of Miletus, often called the first philosopher in the Western tradition, working in the 6th century before the Common Era, reportedly held that all things are full of gods or full of soul, a phrase later thinkers interpreted as an early, if vague, panpsychist intuition, the idea that even apparently inert matter, like a lodestone that attracts iron, might possess some rudimentary form of animating principle. A century or so later, Anaxagoras proposed that mind, which he called nous, was mixed into all things to varying degrees, providing the ordering principle of the cosmos, though as more mind became concentrated in some things than others, those things became more capable of the kind of ordered, purposeful behavior we associate with living creatures. The idea resurfaces at several later points in Western philosophy. In the late 17th century, the German philosopher and mathematician Gottfried Wilhelm Leibniz, working independently of and roughly contemporaneously with Spinoza, developed a strikingly panpsychist metaphysics centered on what he called monads, simple, indivisible, non-physical substances that he argued were the true, fundamental units of reality, each one possessing some degree of perception and appetite, however dim, with more complex monads, like those constituting a human soul, possessing clearer and more organized perception than simpler ones, like those constituting a rock or a drop of water. Leibniz's system was intricate and, on its own terms, an attempt to solve serious problems in the physics and metaphysics of his day, not simply a piece of mysticism, though it has always sat somewhat outside the scientific mainstream. In the 19th century, the English mathematician and philosopher William Kingdon Clifford, whose work in geometry also influenced Einstein's later general theory of relativity, argued for a position sometimes called mind stuff theory, closely related to what is today called non-emergentism or Russellian monism. Clifford's argument, in simplified form, runs like this: we know, with as much confidence as we know anything, that complex human consciousness exists and that it is somehow connected to the physical brain. We also know that brains evolved gradually through natural selection from simpler nervous systems, which evolved in turn from even simpler biological structures, all the way back to single-celled organisms with no nervous system at all. Clifford, along with later thinkers who developed similar arguments, questioned whether it makes sense for a genuinely novel property, consciousness itself, to appear suddenly at some specific point along this gradual evolutionary continuum with absolutely nothing of the same basic kind present at any earlier stage. If evolution is a story of complex properties, gradually built up out of combinations of simpler properties of the same fundamental kind, the argument goes, then perhaps some exceedingly simple form of proto-experience, nothing like full human consciousness, but some faint precursor of it, must already be present in the basic constituents that combine to form nervous systems, rather than experience appearing from literally nothing partway through the evolutionary story. This kind of reasoning is sometimes called the combination problem in reverse, or the argument from evolutionary continuity, and it has been picked up and refined by contemporary philosophers, most notably Galen Strawson, who has argued forcefully that physicalism, if it is to remain a coherent, non-mysterious position, is essentially committed to some form of panpsychism, because otherwise it must accept that consciousness emerges from purely non-experiential matter in a way that is, in Strawson's view, no less mysterious than traditional dualism was, perhaps more so. Other contemporary philosophers, including Philip Goff, whose books have brought these ideas to to a wider public audience over the past decade, have developed detailed versions of this position, often under the label Russellian monism, named for the 20th century philosopher Bertrand Russell, who observed that physics describes the relational, structural, mathematical behavior of matter, how it interacts and moves, but is curiously silent about the intrinsic nature of matter itself, what it is like to be the stuff that physics describes from the outside. Russellian panpsychists propose that this intrinsic nature, whatever physics leaves undescribed, might just be experience itself, however minimal, meaning that physics and panpsychism are not necessarily in conflict. They may simply be describing two different aspects of the same underlying reality: the outer, structural aspect and the inner, experiential aspect, an idea with clear echoes of Spinoza's dual-aspect monism from 3 centuries earlier. It is important to note here that this contemporary philosophical panpsychism is a fairly careful, minimal, and technical position. It does not typically claim that individual electrons think, plan, or have anything resembling human-style thoughts, emotions, or self-awareness. It claims, much more modestly, that even the most basic physical entities might have some infinitesimally simple form of intrinsic experience, so minimal that the word experience almost strains to describe it, and that this minimal proto-experience, when combined and organized in sufficiently complex ways, as in a brain, somehow gives rise to the rich, unified, complex consciousness we are familiar with. And this brings us to what is widely regarded, even by philosophers sympathetic to panpsychism, as the single greatest unsolved problem the view faces: the combination problem. If a brain is made of an enormous number of individual particles, each supposedly possessing its own tiny, separate, minimal experience, how do all those separate micro-experiences combine into the single, unified experience of, say, seeing a sunset, an experience that clearly is not simply an enormous pile of countless, unconnected micro-experiences happening to occur near each other? Ordinary physical combination, the way small parts combine to form larger physical structures, is well understood in physics and chemistry, but it is far from clear how subjective experiences, as opposed to physical properties, could combine in an analogous way. Since combining perspectives seems different in kind from combining physical building blocks, philosophers have proposed a number of possible solutions, some drawing on more sophisticated mathematical structures, some drawing on ideas closer to integrated information theory's account of integration. But no solution to the combination problem currently commands anything close to consensus, even among philosophers who otherwise find panpsychism attractive. It remains, honestly, one of the largest open problems in this entire area of philosophy, and any account of panpsychism that skips past it is skipping past the hardest part. Panpsychism's arguments are mostly philosophical, resting on reasoning about evolution, combination, and the intrinsic nature of matter, rather than on any specific experimental result. Quantum mechanics is different. It is one of the most rigorously tested physical theories ever developed, confirmed to extraordinary precision across an enormous range of experiments, and yet it contains, at its foundations, a genuine and still unresolved conceptual puzzle about the role of measurement and observation. This puzzle has been a magnet for speculation about consciousness for close to a century, so it is worth walking through carefully and slowly, separating what the physics actually establishes from what has been layered on top of it by more speculative interpretation. The puzzle can be introduced through the famous double-slit experiment, first performed in a simple form by Thomas Young in the early 1800s to study light, and later repeated with individual particles of matter, such as electrons, in the 20th century. In its modern form, the experiment works like this. A barrier with two narrow parallel slits is placed in front of a detector screen, and a source fires particles, one at a time, toward the barrier. If you simply covered one slit, you would expect the particles passing through the remaining open slit to build up, over time, into a single band on the detector screen, roughly where you would expect from ordinary, everyday intuition about tiny projectiles. And if you open both slits, ordinary intuition suggests you should simply see two overlapping bands, one behind each slit. That is not what happens. When both slits are open and no attempt is made to detect which slit each individual particle passes through, the particles build up over many repetitions into an interference pattern, a series of alternating bright and dark bands of exactly the kind you would get if two overlapping waves, rather than discrete particles, had passed through both slits simultaneously and interfered with each other, reinforcing in some places and canceling in others. This is deeply strange, because the particles are fired one at a time, so there is nothing else present for an individual electron to interfere with except, it seems, itself, or rather, some wave-like aspect of its own behavior, described by what physicists call its wave function, a mathematical object that assigns a probability to each possible outcome of a measurement. The puzzle deepens further still. If you place a detector at the slits themselves, so that you can determine for each individual particle which slit it actually went through, the interference pattern disappears entirely, and the particles behave exactly as ordinary, classical projectiles would, building up two simple bands rather than an interference pattern, simply gaining which path information, finding out which slit each particle used, destroys the wave-like interference behavior. This effect has been demonstrated repeatedly and is not in scientific dispute. What is in dispute, and has been since the theory's earliest days in the 1920s, is how to interpret it. What, physically, is actually happening? The mathematics of quantum mechanics describes a particle, before it is measured, as existing in what is called a superposition, a state in which multiple possible outcomes are all simultaneously present in the wave function, each with a certain probability, rather than the particle having one single, definite, but simply unknown, classical property, in the way a coin under your hand is definitely heads or tails even before you look. Quantum superposition appears to be genuinely different from that kind of ordinary ignorance, a difference confirmed by a set of results developed theoretically by the physicist John Stuart Bell in the 1960s and tested experimentally with increasing precision from the 1970s onward, work that was recognized with the Nobel Prize in Physics, awarded in 2022 to Alan Aspect, John Clauser, and Anton Zeilinger for their experimental tests of these predictions using entangled particles. These experiments rule out, with high confidence, a broad class of theories in which particles simply have hidden, predetermined, classical properties all along that we are merely ignorant of, and confirm that the strange, probabilistic, seemingly non-local character of quantum mechanics is a genuine feature of nature, not a placeholder for our incomplete knowledge. The open question, called the measurement problem, is what happens at the moment a measurement occurs, the moment the superposition of multiple possibilities apparently resolves into one single, definite, observed outcome, a process often loosely called the collapse of the wave function. The mathematics of quantum mechanics describes superpositions evolving smoothly and predictably over time, right up until a measurement is made, but the theory, in its bare mathematical form, does not clearly specify what physically constitutes a measurement or why measurement should produce a single definite outcome rather than a continuing superposition. This is a genuine, unresolved foundational puzzle in physics, discussed seriously by working physicists, and it has led to several distinct interpretations, each consistent with all existing experimental data, but each telling a very different story about what is actually going on. The oldest and historically most influential interpretation associated with the physicists Niels Bohr and Werner Heisenberg, and often called the Copenhagen interpretation, treats the wave function as a description of our knowledge of a system's possible outcomes and largely declines to ask what is happening physically during measurement, treating the measurement process itself as a kind of primitive, unanalyzed step where classical, definite outcomes appear without attempting a deeper mechanical explanation. Historically, some of the language used by Bohr and others emphasize the special role of observation and measuring instruments, which is part of where popular claims about consciousness causing collapse first took root, though it is worth being clear that Bohr's own concern was primarily about the role of macroscopic, classical measuring apparatus, not about consciousness or subjective awareness specifically. A quite different interpretation, called the many worlds interpretation, first proposed by the physicist Hugh Everett in the 1950s, takes the mathematics completely at face value and denies that collapse happens at all. Instead, on this view, every possible outcome of a quantum measurement actually occurs, each in its own branching, non-communicating version of reality, and what we experience as a single definite outcome is simply the branch we happen to find ourselves in, with countless other branches containing versions of us who observed the other outcomes, existing in parallel but permanently inaccessible to us. This interpretation requires no special role for observation or consciousness at all, since branching happens everywhere, all the time, regardless of whether anyone is watching, and it has a significant, though far from universal, following among physicists today, precisely because it avoids adding any special, unexplained collapse process to the theory's clean mathematics. A third significant interpretation, called pilot wave theory or Bohmian mechanics, developed by Louis de Broglie and later revived and extended by David Bohm in the 1950s, proposes that particles do have definite positions at all times, guided along by an accompanying wave called the pilot wave that is genuinely non-local, meaning it can be instantaneously influenced by events far away, but which is not itself directly observable. On this view, particles are always somewhere definite, and the apparent strangeness of quantum mechanics arises entirely from the peculiar, holistic behavior of the guiding wave, not from any need to invoke observation or measurement as special. A fourth family of approaches, called objective collapse theories, proposes modifying the mathematics of quantum mechanics itself, adding a small, genuinely random physical process that causes superpositions to spontaneously collapse on their own after enough time or mass is involved, entirely independent of whether any observation occurs, with the collapse becoming effectively certain and near instantaneous once a system becomes large enough, which is part of why everyday, macroscopic objects like tables and chairs do not seem to sit around in visible superpositions the way individual particles do. None of these four interpretations nor several others not covered here, currently has decisive experimental support over the others, since they are all constructed, by design, to reproduce the same observable predictions as standard quantum mechanics in every experiment performed so far, differing only in the deeper story told about what is happening beneath those observations. This is an unusual and genuinely interesting situation in physics, a case where the equations are extraordinarily well tested and almost universally agreed upon, while the underlying physical picture those equations are describing remains a matter of active, serious, ongoing debate among physicists and philosophers of physics. It is precisely this open space at the foundations of one of science's best-tested theories that has made quantum mechanics such fertile, if often misused, territory for speculation about the relationship between mind and matter, a thread we will pick up next. Given this genuine open question about the role of measurement, it is easy to see why the idea that consciousness itself causes quantum collapse has appealed to some physicists and philosophers over the decades, and why it appeals even more strongly to popular writers looking for a bridge between mind and physics. The idea has a real, if narrow, pedigree within physics. The mathematician John von Neumann, in his foundational 1932 treatment of quantum mechanics, noted that the boundary between the quantum system being measured and the classical measuring apparatus doing the measuring can, mathematically, be drawn almost anywhere, including, in principle, at the point where a signal reaches a conscious observer's perception. The physicist Eugene Wigner extended this observation in the 1960s with a thought experiment now called Wigner's Friend, in which a friend inside a sealed laboratory measures a quantum system, while Wigner, waiting outside, treats the friend, the measuring apparatus, and the quantum system all together as one larger system still in superposition until Wigner himself learns the result. Wigner speculated, for a time, that consciousness might be what ultimately resolves this chain of ambiguity, though he later distanced himself from that specific conclusion as the field developed, and this thought experiment remains an active subject of theoretical and even experimental research today, though generally now explored without invoking consciousness specifically, focusing instead on more precise questions about whether different observers can consistently agree on the facts of a shared quantum experiment. It is important, however, to be very clear about where mainstream physics currently stands. The overwhelming majority of physicists working on the foundations of quantum mechanics today do not think consciousness plays any special causal role in collapse or in resolving superpositions, and this is not merely a matter of preference or convention. There are strong physical reasons for this consensus. Decoherence, a well-understood and experimentally confirmed physical process, explains a great deal of why superpositions appear to vanish for macroscopic and even many microscopic systems without needing to invoke observation or awareness at all. Decoherence occurs whenever a quantum system interacts, even very slightly, with its surrounding environment, air molecules, stray photons, the measuring apparatus itself, causing the delicate interference effects that produce superposition behavior to rapidly and effectively disappear from any local, practical perspective, entangling the system with its environment in a way that makes the original interference pattern permanently unrecoverable for any realistic observer, whether that observer is conscious, a simple mechanical detector, or nothing at all. Decoherence happens extremely fast, and it happens whether or not any conscious being is present, watching or even exists anywhere nearby. This is a major reason most physicists consider consciousness-causing collapse to be an unnecessary and poorly motivated addition to the theory, since decoherence already accounts for why we do not observe interference effects in everyday macroscopic objects without requiring any special role for minds. A more recent and considerably more specific proposal linking quantum mechanics directly to consciousness in the brain is the theory known as orchestrated objective reduction, developed jointly by the physicist and mathematician Roger Penrose and the anesthesiologist Stuart Hameroff beginning in the early 1990s. This theory proposes that consciousness arises from quantum computations occurring inside microtubules, tiny protein structures found within the internal skeleton of neurons, and that these quantum processes are periodically and spontaneously terminated by a process Penrose had separately proposed on entirely different grounds. Related to quantum gravity, the idea that gravity itself might be responsible for objectively collapsing quantum superpositions once enough mass and energy is involved, rather than collapse being caused by ordinary environmental decoherence or, indeed, by consciousness. This is a genuinely serious and detailed theoretical proposal developed by credentialed scientists, and it deserves to be discussed honestly rather than dismissed out of hand. But it is also fair and important for accuracy to say that it remains a minority position, viewed with considerable skepticism by most physicists and neuroscientists for several specific and well-articulated reasons. The most serious objection, raised prominently by the physicist Max Tegmark in a widely cited paper published in the year 2000, concerns timescales. Quantum superpositions in warm, wet, densely interacting biological environments like the interior of a living cell are expected, based on well-established decoherence physics, to be destroyed by environmental interaction extraordinarily quickly on timescales many orders of magnitude shorter than the timescales at which neurons actually fire and process information. Tegmark's calculations suggested that any quantum coherence in microtubules would decohere in a small fraction of the time it takes a single neuron to complete even the fastest steps of its ordinary electrochemical signaling, making it very difficult to see how such fleeting quantum states could meaningfully influence brain function on the timescales relevant to actual cognition and behavior. Proponents of orchestrated objective reduction have offered responses to this objection, proposing possible physical mechanisms involving ordered water molecules or particular vibrational modes within the microtubule structure that might shield quantum coherence from environmental decoherence longer than naive estimates suggest, and some later experimental work has reported observing longer-lived quantum-like vibrational effects in microtubule structures than originally expected, though these findings remain contested and have not resolved the broader skepticism. As things currently stand, orchestrated objective reduction remains an active but distinctly minority research program taken seriously by a relatively small number of specialists, rather than an accepted or well-confirmed account of how consciousness works, and it would be inaccurate to present it as anything more settled than that. A separate and looser line of quantum speculation, distinct from any specific mechanism, like orchestrated objective reduction, draws an analogy between quantum entanglement and the deep interconnectedness sometimes proposed by panpsychist philosophers. Entanglement is a real and thoroughly confirmed quantum phenomenon in which two or more particles are prepared in such a way that measuring a property of one particle instantly correlates with the outcome of measuring the corresponding property of the other. No matter how far apart the two particles are separated, a correlation Einstein famously found deeply troubling once describing it in a private letter rather than a formal quote for a scientific audience, as involving a kind of spooky influence at a distance, a phrase that has stuck in popular usage ever since. It is tempting, and this temptation shows up frequently in popular writing on the subject, to describe entangled particles as somehow monitoring or communicating with each other, and from there, to suggest that this monitoring represents some extremely minimal form of proto-consciousness distributed throughout the universe, wherever entanglement occurs, which, given how ubiquitous entanglement is at the quantum scale, would be essentially everywhere. It is worth being precise here, because this is exactly the kind of claim where loose analogy can be mistaken for established physics. Entanglement does not involve any actual signal, information, or influence traveling between the two particles at the moment of measurement, a fact confirmed by, among other things, the no communication theorem, a rigorously proven result in quantum theory, showing that entanglement alone cannot be used to send usable information faster than the speed of light, or indeed at all, between separated parties. The correlations revealed by entanglement are real and genuinely strange from the perspective of everyday intuition about separate, independent objects, but describing this as monitoring in anything like the sense that word carries when we talk about attention, awareness, or the most minimal form of experience, is a poetic and philosophical extension of the physics, not a description the physics itself requires or supports. Serious philosophers who explore quantum approaches to panpsychism, including some of the Russellian monists mentioned earlier, tend to be considerably more careful and qualified in how they draw this connection than popular treatments often are, generally presenting it as one possible avenue worth exploring within a much larger, still unresolved philosophical project, rather than as a demonstrated finding. One of the most striking and frequently cited figures in this whole conversation is the American theoretical physicist John Archibald Wheeler, a towering figure in 20th century physics who coined the terms black hole and wormhole, and who spent much of his later career thinking carefully and publicly about the philosophical foundations of quantum mechanics. Wheeler is closely associated with an idea he called the participatory universe, and with a related, more precisely defined proposal called the participatory anthropic principle, developed and discussed particularly from the 1970s through the 2000s. Wheeler's thinking grew directly out of a real and clever experiment he proposed, called the delayed choice experiment, which extends the basic logic of the double-slit experiment described earlier into more startling territory. In Wheeler's thought experiment, later realized in actual laboratory form using photons and, in a striking extension, using light from distant astronomical sources, an experimenter can choose whether or not to gather which path information about a particle's journey through an interferometer only after the particle has already, in some sense, already passed the point where it would have had to behave either like a wave or like a particle in order to reach the detector. Actual experiments of this kind, performed with genuine photons in real laboratories, beginning in the 1980s and refined many times since, confirm that the choice made at the very last moment, after the particle appears to have already committed to its path, still determines whether an interference pattern appears or not, exactly as quantum mechanics predicts. This is a real, repeatedly confirmed experimental result, not merely a thought experiment, though it is worth clarifying precisely what it does and does not show. It does not show that a later choice reaches backward in time to change a particle's past, in the sense of altering some already fixed, definite history. Rather, it shows that it is misleading to think of the particle as having had a definite, classical, wave-like or particle-like nature all along, independent of how it is eventually measured. The measurement choice, whenever it is made, is part of determining which description, wave or particle, correctly applies to the whole process, from source to detector, rather than the choice reaching back to change a separate, prior, already settled fact. Wheeler took this and related results as suggesting something quite radical about the relationship between observation and reality at the deepest level. His participatory anthropic principle proposed that the universe, at a fundamental level, exists in a kind of open, undetermined state of possibility, and that observation, by conscious observing participants, plays an essential role in bringing definite facts about reality into being, not merely learning about facts that were already fully determined beforehand. Wheeler sometimes illustrated this with a playful analogy to a guessing game, in which the answer to a question is not fixed in advance but is generated, in some sense, only through the process of being asked and answered. He suggested that this participatory quality might apply not only to laboratory experiments happening today, but more provocatively to observations we make of very distant, ancient light. For instance, light from quasars billions of years old, raising the striking and admittedly strange-sounding suggestion that present-day acts of observation might, in some carefully qualified sense, play a role in the nature of quantum events from the deep cosmic past. Though Wheeler was careful to frame this in terms of retroactively determining which description applies, rather than physically altering the past, it is important to be clear, again, about the current scientific status of this idea. Wheeler was a serious, highly respected physicist, and the participatory anthropic principle grew out of real, well-confirmed, experimental physics. The delayed choice experiments themselves are not in dispute, but the participatory anthropic principle as a broader, philosophical interpretation of what those experiments mean for the ultimate nature of reality and the role of consciousness within it is Wheeler's own philosophical extrapolation from the physics, not itself a directly tested or broadly accepted scientific theory. Most physicists who study the foundations of quantum mechanics today would say that Wheeler's delayed choice experiments are beautifully confirmed and genuinely challenge naive, classical intuitions about a fixed, independent reality existing separately from measurement, while stopping well short of endorsing the specific idea that consciousness, as opposed to measurement or interaction more generally, is doing the essential work. Many physicists would point out that these experiments work the same way regardless of whether a conscious human being ever looks at the resulting data, so long as a measuring device of some kind registers a definite outcome, which suggests that whatever is special about measurement in quantum mechanics need not depend on consciousness specifically, echoing the same point raised earlier about decoherence. Wheeler's ideas remain influential and are taken seriously as a genuinely thought-provoking philosophical position within the foundations of physics, discussed respectfully in serious academic literature, but they represent one interpretive possibility among several, not a settled conclusion, and it would be inaccurate to present the participatory anthropic principle as an established finding, rather than as one of several live, contested philosophical positions physicists hold about what quantum mechanics ultimately means. There is a broader lesson worth drawing out here, one that will keep resurfacing throughout the rest of this program. Quantum mechanics really does contain, at its foundations, a genuine and unresolved puzzle about measurement and observation, one of the deepest open questions in all of physics. That puzzle is real, and it is entirely reasonable to find it fascinating, even a little unsettling. But the puzzle being real and unresolved does not, by itself, license any particular claim about consciousness being the special ingredient that resolves it. Several serious interpretations of quantum mechanics resolve the measurement problem without any special role for consciousness at all, and the interpretations that have historically flirted with a special role for the observer, from von Neumann and Wigner through to Wheeler, have generally been offered as one serious possibility among several competing interpretations, carefully qualified by their own originators, rather than as demonstrated fact. Being honest about that distinction between a genuine open scientific question and a specific, more speculative answer to it is part of what makes this whole area of science so interesting to think about carefully, rather than simply exciting to skim past. Let us come back down from the foundations of physics to the brain, and to a second major scientific theory of consciousness, one that developed somewhat independently of integrated information theory and offers a genuinely different picture of what is going on, even though the two theories were, as mentioned earlier, tested directly against each other in recent years. Global workspace theory has its roots in work by the psychologist Bernard Bars in the 1980s, and it was later developed further with a much more detailed neuroscientific grounding by the cognitive neuroscientist and physicist Stanislas Dehaene and his collaborators from the 1990s onward. The central metaphor of the theory is a kind of theater of the mind. At any given moment, the brain is carrying out an enormous number of specialized processes in parallel, mostly unconsciously: visual processing, auditory processing, motor planning, memory retrieval, emotional evaluation, and so on, each handled by its own specialized, largely independent neural circuitry, operating most of the time entirely outside of conscious awareness. Global workspace theory proposes that consciousness arises when information from one or more of these specialized processes is selected and broadcast widely across the brain, made globally available to many other systems at once, roughly analogous to a single actor stepping into a spotlight on a stage, becoming visible not just to themselves, but to the entire audience and to every other actor in the wings, all of whom can then use that information to inform their own behavior. On this view, the vast majority of brain processing remains unconscious, not because it is somehow deficient or too simple, but because it stays local, confined to its own specialized circuit, never achieving that wide global broadcast. Consciousness, on this account, is closely tied to a specific kind of large-scale, long-range communication across widely separated brain regions, particularly involving connections between sensory processing areas and a distributed network of regions, prominently including parts of the frontal and parietal cortex that appear to support this kind of broad, flexible cross-system integration. Dehaene and his collaborators have identified a number of measurable neural signatures associated with this global broadcasting process, including a distinctive late, widespread pattern of electrical brain activity, sometimes called the P300 signal, that appears reliably when a stimulus becomes consciously reportable, and a related, sudden, large-scale ignition of activity across widely distributed cortical regions, which contrasts with the much more limited, localized brain response that occurs when the same stimulus is presented so briefly or so faintly that a person does not consciously notice it at all, even though their brain has, in a real, measurable, but unconscious sense, still processed it. Notice how differently global workspace theory frames the central question compared to integrated information theory. Integrated information theory asks about the intrinsic causal structure of a system, in principle applying, at least mathematically, to almost any sufficiently integrated system in the universe, including, hypothetically, systems entirely unlike brains. Global workspace theory, by contrast, is much more specifically tied to the particular architecture of biological brains, particularly to the existence of a widely broadcasting, integrating network with specific functional properties, and it says considerably less about whether other kinds of physical systems lacking this specific broadcast architecture could be conscious in any degree at all. These are genuinely different pictures of what consciousness fundamentally is, one emphasizing intrinsic, structural integration wherever it occurs, the other emphasizing a specific kind of functional, brain-like information broadcasting architecture, and it is precisely because they make different and, in principle, testable predictions that the adversarial collaboration mentioned earlier was designed using careful brain imaging experiments to see which theories' specific predictions held up better against real neural data gathered under tightly controlled conditions across several independent laboratories. The results of that large, collaborative study, again, were genuinely mixed rather than a clean victory for either side. Some predictions specific to global workspace theory, particularly concerning where and when certain signatures of conscious perception should appear in the frontal cortex, were not as clearly supported by the data as the theory's proponents had expected, and some predictions specific to integrated information theory, particularly concerning sustained, specific patterns of connectivity in posterior regions of the cortex throughout a conscious experience, were also not fully supported. This outcome has led a number of researchers in the field to suggest that the eventual, mature scientific theory of consciousness, whenever it arrives, may need to incorporate genuine insights from both frameworks and possibly from other approaches as well, including higher-order theories, which propose that a mental state becomes conscious specifically when the brain forms a further, higher-order representation about that mental state, essentially a kind of internal awareness of being aware, a distinct proposal with its own body of supporting and challenging evidence that space here does not allow covering in full detail. What all of this recent work makes clear, and what is worth sitting with, rather than rushing past, is that consciousness science today is a genuinely active, unsettled, rapidly evolving field with multiple serious, well-evidenced, competing theories still very much in play, exactly the kind of situation, honestly, that tends to produce real scientific progress over time, even when it does not yet produce a single, tidy, final answer. This is a natural point to widen the picture and ask a related and in some ways more approachable question, rather than asking whether consciousness might extend all the way down to particles and quantum fields. We can ask a more modest version of the same basic question: how widely is consciousness distributed among the living creatures already here on Earth, creatures whose brains and nervous systems we can actually study directly? For a long stretch of the 20th century, especially under the influence of the behaviorist school of psychology, many scientists were quite cautious, sometimes to the point of outright skepticism, about attributing rich inner experience to any animal other than humans, partly because subjective experience is, by its nature, not directly observable from the outside, and partly out of a reasonable methodological caution about projecting human-like inner states onto creatures that cannot describe their experience to us in words. That caution has loosened considerably over the past few decades as accumulating evidence from comparative neuroscience, cognitive ethology, and animal behavior research has made the case for animal consciousness, at least in many species, increasingly difficult to responsibly dismiss. A particularly interesting case, and one the source material for this kind of discussion often highlights, involves cephalopods, the group of mollusks that includes octopuses, cuttlefish, and squid. Octopuses are especially striking because their evolutionary lineage diverged from the lineage leading to vertebrates, including humans, an extraordinarily long time ago, roughly 500 million years before the present, meaning that whatever cognitive sophistication octopuses display evolved entirely independently of the vertebrate nervous system through a completely separate evolutionary pathway, making them one of the best available natural experiments in what independently evolved intelligence and complex behavior can look like. Octopuses have been observed in carefully controlled laboratory and field studies to use tools to solve multi-step mechanical puzzles, such as unscrewing jars to reach food inside, to learn by observing other octopuses solve a task, to exhibit distinct individual personalities and behavioral preferences that are stable over time, and to change the color, pattern, and texture of their skin almost instantaneously for camouflage or communication, a feat of coordinated neural and physiological control that remains an active subject of ongoing research. Their nervous systems are also unusually distributed compared to a typical vertebrate, with something like 2/3 of an octopus's neurons located not in its central brain, but out in its 8 arms, each of which is capable of a striking degree of independent, coordinated, sensor-rich behavior, raising genuinely interesting and still not fully resolved scientific questions about how unified or distributed an octopus's overall experience, if it has one, might actually be. This growing body of evidence concerning cephalopods, along with parallel evidence concerning birds, particularly corvids such as crows and ravens, which display tool use, planning for future needs, and apparent understanding of other individuals' perspectives, and evidence concerning mammals more broadly, contributed to a notable public statement in the scientific community called the Cambridge Declaration on Consciousness, signed by a group of prominent neuroscientists at a conference held at the University of Cambridge in July of the year 2012. The declaration stated that the weight of scientific evidence indicates that many non-human animals, including all mammals and birds, and many other creatures, including octopuses, possess the neurological substrates that generate consciousness, and that humans are not unique in this regard. It is worth being precise about what this kind of scientific statement does and does not claim. It is a considered judgment by a group of specialists about the weight of existing neurological and behavioral evidence, rather than a direct measurement or proof of subjective experience in these animals, since, as with the hard problem discussed earlier, no external measurement can directly access another creature's private, subjective experience, whether that creature is human or not. But it reflects a genuine and significant shift in the scientific mainstream's confidence about how widely distributed some meaningful form of consciousness likely is among Earth's animals, a shift driven by real, accumulating behavioral and neurological evidence not by philosophical speculation alone. This question of how consciousness is distributed among living things connects in an interesting way back to the non-emergentist argument from evolutionary continuity discussed earlier in connection with William Kingdon Clifford. If consciousness turns out to be present in some real and scientifically defensible sense, not only in humans but in birds, in mammals broadly, and in octopuses whose nervous systems evolved along an entirely separate evolutionary branch, this at least weakens the intuitive picture of consciousness as a single, sudden, uniquely human achievement, and lends some further, if still inconclusive, support to the general idea that whatever gives rise to consciousness may be a graded, widely distributed capacity across the animal kingdom, appearing in different forms and to different degrees, depending on the complexity and organization of a given nervous system, rather than switching on abruptly at any single evolutionary threshold. This is, again, quite a different and much more modest claim than the panpsychist proposal that individual particles, or atoms, might have some minimal proto-experience. It stays within the domain of nervous systems and observable behavior, and it remains itself an area of active and sometimes contested scientific research, particularly regarding simpler nervous systems, such as those of insects, where the question of whether and to what degree consciousness is present remains genuinely unresolved and is the subject of ongoing careful study, including recent work attempting to apply frameworks like integrated information theory to insect brains, without yet producing a settled answer. There is another rich seam of consciousness research worth spending time with, one that approaches the question not by asking where consciousness is distributed across species, but by studying what happens to ordinary human consciousness when it is deliberately altered, whether through long-practiced mental training, through specific chemical compounds, or through the many gradual and sudden changes that occur across the boundary between waking and sleep. Altered states research has become an increasingly respected and rigorously studied branch of neuroscience over the past 2 or 3 decades, offering a valuable natural laboratory for probing which brain processes are truly necessary for ordinary waking consciousness. By observing what changes and what stays constant when consciousness itself takes on an unusual character. Meditation research provides one clear example. Practices of sustained, trained attention found in various forms across many contemplative traditions, particularly certain Buddhist traditions that have been most extensively studied by Western neuroscience, have been shown in a substantial and steadily growing body of brain imaging research to produce measurable, reproducible changes in brain activity, and with long-term practice, even in brain structure, long-term meditators studied using functional brain imaging show altered patterns of activity in a network of brain regions sometimes called the default mode network, a set of interconnected regions that tends to be most active during mind-wandering, self-referential thought, and the kind of unfocused inner narration many people experience during ordinary waking rest, and least active during focused, externally directed attention. Reduced default mode network activity, along with altered connectivity between this network and other brain regions, has been associated in numerous studies with the subjective reports, common among experienced meditators, of a diminished sense of a separate, narrating self and an increased sense of open, spacious, less self-centered awareness during deep meditative states. This research does not, by itself, resolve any of the deep, philosophical questions about the ultimate nature of consciousness discussed earlier in this program, but it does provide some of the clearest available evidence that the ordinary, everyday sense of being a continuous, separate self is itself a specific, identifiable brain process generated by particular, measurable neural activity, rather than a fixed, unquestionable background fact of experience, since that sense of self can be measurably altered and, in the reports of experienced practitioners, substantially reduced through sustained mental training alone. A second and, in recent years, especially active area of altered states research involves classic psychedelic compounds, including psilocybin, the active compound found in certain mushrooms, and lysergic acid diethylamide, more commonly known by its abbreviation, which itself is one of the few genuinely necessary exceptions to full spelling of terms in careful spoken science communication, usually pronounced letter by letter, after several decades during which legal and regulatory restrictions sharply limited scientific research into these compounds. A renewed wave of carefully controlled clinical research, beginning in the early 2000s and expanding substantially over the past 15 years at research centers, including Johns Hopkins University, Imperial College London, and other institutions, has produced a considerable body of peer-reviewed findings. Brain imaging studies conducted under these compounds have consistently found a marked, temporary disruption and desynchronization of the same default mode network implicated in meditation research, along with, somewhat counterintuitively, an overall increase in the diversity and, by some measures, the complexity of communication between brain regions that do not typically communicate strongly with each other during ordinary waking consciousness. Some researchers have specifically applied measures inspired by integrated information theory to brain activity recorded during psychedelic states, reporting, in some studies, increased measures of neural signal diversity or complexity compared to ordinary waking consciousness, an intriguing and actively debated finding, given that subjective reports during these states often describe an intensely rich, vivid, sometimes overwhelming quality of experience, though it is worth being cautious here, since increased measured complexity by a particular metric is not the same thing as a confirmed, agreed-upon measurement of a greater quantity of consciousness itself, and this remains a genuinely open and actively researched question rather than a settled finding. Clinically, this same renewed wave of research has produced promising, and in some specific cases quite strong, evidence for the therapeutic potential of carefully administered psychedelic compounds, combined with structured psychological support in treating conditions including severe treatment-resistant depression and, specifically, the psychological distress associated with terminal illness, findings that have contributed to regulatory bodies in several countries granting expedited or breakthrough designations for continued clinical research and, in a small number of jurisdictions, limited approved therapeutic use under medical supervision. None of this research settles any of the deeper philosophical questions raised earlier in this program about the ultimate nature of consciousness, and responsible researchers in the field are generally careful to separate the clinical and neuroscientific findings, which rest on real, replicated data, from the more speculative philosophical or spiritual interpretations that research participants sometimes offer of their own experiences, interpretations that are personally meaningful and worth taking seriously as reports of subjective experience, but which are not, themselves, scientific findings about the nature of reality. A further and, in some ways, more clinically urgent area of altered states research concerns disorders of consciousness following severe brain injury, including the vegetative state, now more often called unresponsive wakefulness syndrome in clinical settings, and the minimally conscious state, conditions in which a patient may show cycles of apparent wakefulness, opening their eyes and displaying basic reflexes without clear behavioral evidence of awareness or with only inconsistent, ambiguous signs of it. A landmark study published in the New England Journal of Medicine in the year 2006, led by the neuroscientist Adrian Owen, used functional brain imaging to ask a patient diagnosed as being in a vegetative state, showing no reliable outward behavioral signs of awareness, to imagine playing tennis, and separately to imagine walking through the rooms of her own house, two mental tasks known from prior research with healthy volunteers to reliably activate two quite distinct and separately identifiable patterns of brain activity. The patient's brain activity recorded during this task closely matched the appropriate pattern for each imagined task, providing striking evidence that some meaningful form of conscious awareness and willful mental control was present, despite a complete absence of outward behavioral signs that would have been detectable through ordinary bedside clinical examination alone. This finding, and the substantial body of related research it helped launch, has real and serious clinical stakes, since it suggests that a meaningful fraction of patients diagnosed as vegetative based on behavioral examination alone may, in fact, retain some significant degree of conscious awareness, a possibility with direct and weighty implications for how such patients are cared for, communicated with, and included in decisions about their own treatment, and it remains an active area of clinical neuroscience research, including ongoing efforts to develop more accessible, lower-cost, bedside methods of detecting this kind of covert consciousness beyond specialized brain imaging centers. Having spent this much time with the brain, with quantum physics, and with the philosophical arguments for and against panpsychism, it is worth pulling back for a little while to the widest possible scale and asking how the scattered pieces of this discussion relate to the sheer size of the universe those brains happen to be sitting inside. Our sun is one star among an estimated 100 billion to 400 billion stars in the Milky Way galaxy alone, and the Milky Way is, in turn, only one galaxy among a number of galaxies in the observable universe, currently estimated to be somewhere in the range of 200 billion, a figure that has itself been revised across recent decades as telescopes have improved, with some earlier, now largely superseded estimates from deep field surveys conducted in the early 2000s, suggesting numbers as high as a couple of trillion, before more recent analysis, using improved data from instruments, including the Hubble Space Telescope, favored the somewhat lower current estimate. Whichever figure ultimately proves most accurate, the basic point stands regardless. The observable universe contains an almost incomprehensibly large number of stars, and, based on discoveries over the past 3 decades, an even larger number of planets, since most stars appear from the accumulated data of dedicated planet hunting missions, including NASA's Kepler Space Telescope, STENU, launched in 2009, and the more recent Transiting Exoplanet Survey satellite, to host at least one planet, and often several. This sheer scale is part of why many scientists consider it statistically implausible, though certainly not impossible, that Earth is the only place in the universe where consciousness, in whatever form, has arisen. This reasoning, sometimes summarized informally as a version of the Copernican principle, the general historical pattern by which each new discovery has tended to remove humanity from any uniquely privileged position from the center of the solar system to an ordinary position within an ordinary galaxy among countless others, has real intuitive and historical force. But it is important to be precise about what this argument does and does not establish. Statistical plausibility, based on the sheer number of available planets, is not the same thing as direct evidence. Despite decades of dedicated searching, including the Search for Extraterrestrial Intelligence program, which has used radio telescopes since the 1960s to listen for artificial signals from other star systems, and despite an expanding, increasingly sophisticated search for biosignatures, chemical signs of life, in the atmospheres of exoplanets using instruments including the James Webb Space Telescope, launched in December of 2021, no confirmed evidence of life, let alone consciousness, has yet been found anywhere beyond Earth. The universe may well be teeming with life and even with conscious minds, or it may, despite its vastness, be far sparser in this respect than intuition suggests. A genuine possibility raised by a line of reasoning sometimes called the Fermi paradox, after the physicist Enrico Fermi, who is said to have informally posed the question during a 1950 conversation with colleagues of where everybody is, given how old and vast the universe is, and how much time other civilizations, if they exist in any number, would have had to develop and potentially spread or signal their presence. Both possibilities, a universe rich with minds and a universe where Earth's minds are startlingly rare, remain live and unresolved, and honest science reporting on this topic should resist the temptation to present either one as more than an open question awaiting better evidence. This uncertainty connects back in an interesting way to the panpsychist ideas discussed earlier in this program. If some minimal form of proto-experience really is a fundamental feature of matter itself, present, however faintly, everywhere physical processes occur, then in some very abstract, technical, philosophical sense, the universe would already be, in this specific, limited meaning of the term, saturated with something related to experience everywhere, all the time, entirely independent of whether complex, self-aware, richly conscious life like ours happens to exist anywhere at all. This would be a very different claim from the more familiar science fiction question of whether intelligent civilizations exist elsewhere among the stars. It would not imply that stars, or galaxies, or interstellar clouds of gas and dust have thoughts, plans, emotions, or anything resembling a perspective on their own existence in any way comparable to a human mind, a distinction worth holding onto carefully, since it is exactly the kind of distinction that gets blurred in less careful popular treatments of these ideas, sometimes described loosely as the universe waking up to itself, phrasing that makes for evocative narration but overstates considerably what the underlying philosophical position actually claims. It is genuinely difficult, and this program does not claim otherwise, to know how much weight to give any of this. The gap between the confirmed, well-tested physics of stars and galaxies and the highly speculative philosophical proposal that matter everywhere carries some minimal trace of proto-experience is a very large gap indeed, bridged at present only by philosophical argument rather than empirical measurement. What can honestly be said is that the sheer scale of the universe, the sheer number of stars and planets, and, presumably, the sheer number of possible arrangements of matter gives these old philosophical questions about the extent and origin of consciousness a genuinely vast canvas to play out across, whether or not that canvas is In fact, painted with anything resembling experience beyond the small, warm, richly conscious corners of it we already know about directly. Here on Earth, there is one more current thread worth including before closing, because it has become, over just the last handful of years, one of the more active and unusual arenas where these old questions about consciousness are being asked in a genuinely new context. The question of whether or when artificial systems built from silicon rather than neurons might have any form of inner experience at all. This question has moved fairly rapidly from a topic largely confined to philosophy seminars and science fiction into a subject of serious discussion among computer scientists, neuroscientists, and philosophers working together. Part of what makes it difficult is that the leading scientific theories of consciousness discussed earlier in this program give genuinely different answers, or in some cases decline to give a clear answer at all. When applied to current artificial intelligence systems, global workspace theory, with its emphasis on a specific kind of broad, integrative information sharing architecture modeled on features of biological brains, offers one set of criteria to check a system against, though applying those criteria precisely to the very different internal architecture of a modern large language model built from layered mathematical transformations, processing text rather than anything resembling a biological nervous system is not straightforward, and researchers who have attempted this kind of analysis in recent published work have generally concluded that current systems satisfy few, if any, of the specific architectural indicators the theory would consider important, without being able to rule the possibility out definitively either. Integrated information theory, as discussed earlier, is in principle applicable to any system with the right kind of internal causal structure, but calculating anything resembling a genuine phi value for a modern artificial intelligence system built from architectures generally involving a great deal of fast, largely feed-forward, easily decomposable information processing is not currently practical, and most researchers working directly with the theory have been cautious about drawing strong conclusions either way from current, incomplete methods of estimation. A group of researchers and philosophers, drawing directly on several of the established theories discussed throughout this program, published a widely discussed report in the year 2023 proposing a checklist of specific theory-grounded indicator properties drawn from global workspace theory, higher-order theories, and other established frameworks that a computational system might be expected to display if it possessed some of the specific mechanisms current theories associate with consciousness in biological systems. Applying this checklist to systems available at the time, the authors concluded that no current artificial intelligence system convincingly satisfied more than a handful of these indicators, while noting explicitly that there was no clear, principled technical barrier that would prevent future systems deliberately designed with different architectures from satisfying considerably more of them. This kind of careful, indicator-based approach, rather than a simple yes or no verdict, reflects where serious researchers in this area currently stand, taking the question seriously enough to specify testable, theory-grounded criteria, while being honest that current evidence does not settle the underlying question in either direction, and that our uncertainty here stems partly from the fact that the underlying scientific theories of consciousness themselves, as this whole program has tried to make clear, remain unsettled and still under active development, even when applied to the biological brains we understand best. This uncertainty has real practical stakes, discussed increasingly seriously within the field of artificial intelligence research itself, sometimes under the heading of model welfare, concerning what obligations, if any, might eventually be owed to sufficiently sophisticated artificial systems if there were ever good reason to believe such systems had morally relevant experiences, alongside a great deal of appropriate caution expressed by researchers across the field about the risk of either dismissing the question prematurely, given how much genuine uncertainty remains about consciousness even in well-studied biological systems, or overstating current systems' likely inner lives, well beyond what present evidence or theory actually supports. It is a genuinely open question, being approached, at its best, with the same kind of careful, theory-grounded, evidence-weighing spirit this program has tried to bring to every other question it has covered, rather than with either confident dismissal or confident attribution in either direction. So where does all of this leave us? It leaves us, honestly, with a great deal we still do not know, and it is worth closing by naming some of the most significant open questions plainly, rather than pretending any of them have been resolved along the way. We still do not have an agreed-upon scientific explanation for why physical processes in the brain are accompanied by subjective experience at all. The hard problem introduced near the beginning of this program, and it remains a genuinely contested question, whether that problem will eventually dissolve as neuroscience matures, the way certain older biological mysteries eventually dissolved once their underlying mechanisms were fully understood, or whether it points towards something current physical science, as currently structured, is not yet equipped to explain, requiring some genuinely new theoretical ingredient not yet identified. We still do not have a single, agreed-upon scientific theory of consciousness, with integrated information theory, global workspace theory, higher-order theories, and others each capturing genuine and important aspects of the phenomenon while facing serious, specific, unresolved challenges and recent large-scale, carefully designed experimental collaborations, rather than settling this competition, have so far mainly clarified how much further work remains to be done. We still do not know how widely distributed consciousness, or something meaningfully like it, actually is, whether it extends only to creatures with brains reasonably similar in complexity to our own, or considerably further down into simpler nervous systems, and whether the deeper, more radical panpsychist proposal that some minimal form of proto-experience extends into the basic constituents of matter itself is a genuine insight about the fundamental nature of reality, or an interesting but ultimately mistaken piece of philosophical reasoning, a question that remains, and may for a long while continue to remain, outside what any current experiment can decisively settle one way or the other. We still do not have a resolved, agreed-upon interpretation of what is physically happening during quantum measurement, a genuine and foundational open question in physics itself, entirely independent of consciousness, that continues to generate serious theoretical and experimental work, including ongoing refinements of delayed choice and entanglement experiments, and continued efforts to test the predictions of decoherence, objective collapse theories, and other proposed resolutions with ever greater precision. And we still do not know whether artificial systems, built along entirely different architectural lines than biological brains, could ever come to have anything resembling inner experience, a question that has moved, within just the past few years, from speculative fiction into an active, carefully theorized subject of scientific and philosophical research. None of this uncertainty is a failure of science. If anything, it is closer to the opposite, It reflects just how seriously these questions are now being taken, with careful mathematics, carefully designed experiments, cross-laboratory collaborations, and rigorous philosophical argument, all being brought to bear on a set of questions that, for most of human history, were left almost entirely to religion, myth, and unaided personal reflection. The integration of information across billions of neurons, the strange, still not fully understood relationship between measurement and reality at the heart of quantum mechanics, the astonishing, independently evolved intelligence of a creature as different from us as an octopus, the vast, only partially charted scale of a universe containing hundreds of billions of galaxies each, with hundreds of billions of stars, and the newly urgent question of what, if anything, is happening inside the artificial systems we have only just begun building. All of these threads are still being actively pulled on, in laboratories and in journals, right now, by people who take the difficulty of the question exactly as seriously as it deserves. It is a genuinely remarkable thing that matter arranged in the right way can turn around and wonder about itself, can build instruments to study its own inner workings, can propose and test elaborate theories about the very quality that makes the wondering possible in the first place. Whatever the eventual answer turns out to be, whether consciousness proves to be a specific, rare, hard-won achievement of complex nervous systems, or something considerably more widespread, threaded quietly through far more of the physical world than we currently have any way of confirming, the fact that we can ask the question at all, carefully, patiently, across centuries and across disciplines, and keep making real, if incomplete, progress on it, is itself one of the more quietly extraordinary things about being here, awake, in a universe old and large enough to have produced, eventually, something capable of noticing it and wondering softly what it all is.